Alright, here comes the real-world application of vectors, and this is why I wanted to put this on a different video. It's still with day 3, but these are the real-world problems. Okay, so it says, sketch a vector to predict the path of the golf ball that would result with the given conditions. So the wind, let's put wind, since the sky is blue, we'll put wind as blue. Okay, and notice that the wind, think of L as like the power level, if you will. The power level of the wind is 0, so it's not blowing in any direction whatsoever. So there's no wind for this first example. And straight ahead is what we're going to have a power level of 4. This golfer is going to hit straight ahead a power level of 4. 1, 2, 3, 4 is where this is hitting this vector. So dot with an arrow shows where it began and what direction is it going. Okay, the same over here. So we have a power level of 4, but okay, so let's create that first. Here's the power level of 1, 2, 3, 4, and then there's a wind that's coming. Oops, in blue. Let's do blue. There's a wind that's coming from behind the player. Okay. So if it's coming from behind the player, it's basically aiding the player, and it's helping the player have more power, if you will. So we're going to do that wind right here, tell the tip method, and we're going to have it go straight up too. Okay? So that's what it's going to look like as far as the difference between having wind and the difference between not having wind. Okay? But we want to sketch a vector to predict the path of the ball. So we're just trying to sketch, let me do this in gray, just what's the path of the ball. So here it would be this, and here it would be the entire thing is that resultant vector. Okay? So how can they be described using vectors in a vector sum? You can say that the wind has a vector component of 0, 0. And you can say that the player has a vector component or vector components of 0, 4. So if I were to say the wind plus the player, just like I did in those charts the last video, you're just going to add these straight down, you would get this resultant vector. Otherwise, aka the result. So 0, 4 is, of course, in gray what we highlighted totally. Okay, so let's come over here and do this one. So we have the wind, which traveled at a 0, 2. We had the player that hit with the strength of 4 straight up. And whenever I added these together, I'd have 0, 6, which is, of course, what you see as far as the resultant is concerned here. And again, the resultant is what actually happened, and that's what I have highlighted in gray. Alright, so that's just the beginning. Now, let's not have wind go straight up and down or left or right. We're going to have it looking at different angles and whatnot. So let's say we have a wind that's going to the right with a power level of 6. So notice the arrow on this gauge. So I can already write that the wind is going to have a 6, 0 component vector because of the way that it's traveling to the right. Okay, and think of it like this. If I'm traveling on an x-axis straight to the right, the only thing that's changing is, in fact, that x component. Now I have a 30 degrees to the left. Now here is something new. That means 30 degrees from the left of center, or forward, if you will. Okay, so this is 30 degrees to the left. What direction would that be if I'm talking about from 0 degrees? So here, again, the world revolves around you in this unit. Here is my 0, and if I go all the way here, it's going to be this 90 plus the 30. That would say that the direction that the ball is being hit is going to be 90 plus 30 is 120 degrees. So this is hitting at 120 degrees as far as to the left. Okay? But what I'm wanting to do is I'm wanting to find the components of that. Okay, so if it's hitting at that direction, okay, and then the magnitude is a power of 6. That's the power level that it's hitting at. we're going to say that that's the magnitude, then I can find what are the components of the player, but I'm going to have to do more work. Okay? I'm going to have to do, to get the x, I'm going to have to do the magnitude times the cosine of 120. And then to get the y, I'm going to have to do the magnitude times the sine of 120. Again, just like we did on the tables in the last video, only now we're finally doing it with real-world problems. So 6 times the cosine of 120, and then 6 times the sine of 120. And with the calculator, we get the following pieces. Whoops. We get -3 and then 5.196. So we're going to say -3 is the x, 5.196 is the y, and yes, the resultant vector would be if I added these up together. So you get 3 here, and then 5.196. Okay? So 3 and 5.196 is going to be, as far as the result, hold on just a bit. It's going to be, the wind is a +60, and then we have a negative, yep, sure enough. And then the resultant is going to be, where is it traveling? So, let me highlight something for you. This right here is the player. I'm going to do that in red. Okay, so I don't want you to get confused with this diagram. The wind is the blue. Okay, so as you're doing this, there's a blue wind going on. Okay, and the resultant vector is going to be right here. And this is where this real-world application comes into play. Notice the signs of the resultant vector. It's a positive, positive. So if the world revolves around me and I'm here, I know that it's going to be a resultant saying that it's going to travel somewhere in what would be kind of like that second quadrant piece to it. Okay? This is where that first quadrant. First quadrant comes from that positive, positive. So if I'm adding these vectors, sure enough, from here, this is the pathway that the ball would actually travel. And we're going to call this, say, W plus P, the wind plus the player's vectors. Okay? So let me highlight this in green so that you know where the ball is actually going. And this is the resultant vector of the ball. Okay? So let's describe just a little bit more as far as what we're doing, because we know the resultant vector. With the resultant vector, I know this is not the chart, but if it was, we just found this piece here with the resultant vector. Now, to go backwards to find the directional angle, we'll say the arctangent of 5.196 over 3. And then to find the magnitude, we're just going to do the square root of 3 squared plus 5.196 squared, and then see what we get as far as the magnitude is concerned. Okay, so let's go to the calculator. Arctangent of control divide 5.196 over 3 is going to give us this 59.999. So this angle is about 60 degrees, if you will. Okay, so 59.999 degrees. That means, again, if the world revolves around me right here, from 0 degrees to that resultant vector, it's traveling in relation to the unit circle at 60 degrees. Now let's see how far, which is the resultant, the magnitude, let's see how far it will actually travel. So we're going to do the square root of 3 squared plus 5.196 squared. Take the square root, and the resultant would be 5.999, otherwise 6 is that power level. Okay, so the resultant's magnitude comes out to, let's say, 6. In this case, does it have feet? Does it have units? It does not, but we'll put units. UN for units. So it's traveling 60 degrees, and it's going to go vectors were like feet or miles, then you'd put 6 feet or you'd put 6 miles. But that's the concept as far as what we're doing to get those pieces of what's happening in real life. Okay. So now let's go over here to this other one. It says toward the top right, there's a wind, and you notice the wind. It's going this direction. Okay, it's showing you that vector. The power level is 2. And toward the top right, from this, just these words, you need to assume that it's talking about top right is at this halfway 45-degree angle. Okay, so if this was north, south, east, and west, this is going like northeast. So northeast could be synonymous toward the top right. Okay, so the wind's vector. Let's go ahead and put the wind's vector. So the wind has a power level of 2. So we can say that the magnitude is 2. I'm going to create the chart. The degrees, it's 45 degrees. And then the components are simply going to be, what is that x? What's that 2 times cosine of x? Or 2 times cosine of 45? 2 times the cosine of 45, and then 2 times the sine of 45. And in this case, if I would go to my calculator, I'd get those pieces right there. So I'll put 1.414, 1.414. Okay, now let's do the player's vector. So the player's vector has a power level of 5. It's going 30 degrees to the left. Again, that from 0 degrees, that means this 90 plus the 30, which would give you 120. So we're going to put 120 right here. And then we're going to do the same thing. The magnitude times the cosine, the magnitude times the sine. So we'll say 5 times the cosine of 120, and then 5 times the sine of 120. And going to the calculator, you see negative 2.5 and 4.330. So negative 2.500, if you will, and then 4.330. And now we're going to add them straight down to get our resultant vector. Okay, so let's do our resultant vector. Let's do it this time in purple. Or no, let's do it in brown. So the resultant vector is going to be, let's add these straight down. Right here is what I'm saying. I just didn't want to write over it. So we'll have 1.414 plus a negative 2.5 and a 1.414 plus a 4.330. So from the calculator, these negative 1.086 and 5.744 are the components of the resultant vector. Okay. Now if I want to know what direction it's traveling at, I'm going to do the same. I'm going to take the arctangent of 5.744, the y over the x. And let's see what we get here. Okay? Let's see what we get here as far as what the calculator will give us. So we're going to take the arctangent, control divide of 5.744 over negative 1.086. Now this is what I was talking about. The calculator gives me a negative answer, but I always tell you, I want you to look at this as a positive. Instead of memorizing all those rules and everything depending on what quadrant it's in, I want you to look at this as a positive 79.294 degrees. Okay? And then look at the resultant vector. Okay? So this resultant vector is saying it's going to have a negative, positive piece to it. So a negative x, positive y says it's going to be somewhere in a quote-unquote quadrant 2 location from the origin. And this angle here, this 79, the reason why I want you to look at it as positive is because from this vector to the nearest x-axis is a 79.294 degrees. Okay, it's the reference angle. So if I go from 0 all the way here, the way I'm going to get that is simply subtracting 180 minus this little smidget of 79.294 will give me the answer as far as what direction is this resultant traveling in. So I'll say 180 minus that positive version. Please, when you're doing this, don't make the mistake of saying 180 minus what I got, because that's not going to be correct. It's going to be 180 minus the positive version of this. So remember, the positive version of this, no matter what, we're looking at it as a positive, and then you get 100.706. That is a common mistake. So 100.706 is the directional angle that the ball is going to be traveling at. And then, doing Pythagorean theorem, the square root of parentheses, okay, 1.086, so negative 1.086, parentheses are important because it's negative, and then 5.744. So 5.744, when we find the answer we get 5.8, so 5.846 units is the strength. So it's hit at 100 degrees, okay? Now because this arrow's here, don't assume that that's where it's going. That was the degree to the left of where the player started at. But where it's actually going to go, let's do that in brown. It's going to go 100 degrees. So like from 0 to 100 degrees is probably about right here. And it's going to go a strength of 5.846. So 1, 2, 3, 4, 5.846. So it'll look like something like that. So the resultant vector, let me highlight that in green. These are the components of the resultant vector, and it would be traveling that strength and in that direction. Alright, so the last page of the notes. Looking at the last page of the notes, we're going to look at other real-world problems dealing with the vector addition. Okay? So here F1 and F2 are vectors for the forces, and R is the vector of the result, otherwise the resultant. Okay? So the direction of each vector is still the rotational angle. And again, this is all in relation to where this is 0 degrees, where is it that I'm ending up at with my vector to know that directional angle. And then the magnitude of each vector is associated with the length, and we've talked about this from other places. Alright, so now, again, we have a table to set up everything that is in words, and we're just going to go there and we're going to find the actual speed of the boat and the number of degrees it's taken off course. Okay, so there is a lot of real-world application in here. Let's go step by step. Alright, so let's do B for boat. And you can see that the boat has this heads directly across the river going at 12 miles per hour. So the magnitude is 12, and because it's going straight across the river, its vector is 0 degrees. Again, the world revolves around you, this unit. So from here, if this is my origin, it's traveling at 0 degrees. And you would do 12 times the cosine of 0 in order to get 12. And then you do 12 times the sine of 0 in order to get 0. So the components of the boat vector is, in fact, 12, 0. Okay, C. C is the current of the river. Okay, so the current of the river is traveling, and you can see it with these arrows, it's traveling downward, and the current, it says, is flowing at 17 miles an hour. Okay? So if it's flowing at 17 miles an hour, and that's that magnitude of it, the direction is going to be at this negative 90. Or if you wanted to, you could put 270. Either one, let's go ahead and put 270. Okay? And we're trying to find what are the components. Okay? So the components are going to be 17 times the cosine of 270. and we get 0. Okay. And we're going to do 17 times the sine of 270, and we get negative 17. Now, very, very important right now. I want you to look at the magnitude here. This magnitudes cannot be negative. It's like you can't have a negative 3 feet of rope. Magnitudes have to be positive. So right here, although it's traveling at a component of negative 17, please make sure that you understand that the way you would get the magnitude is to do the a squared plus b squared representation and take the square root, so that the magnitude will always be a positive. Okay? So now, let's go ahead and add straight down. We get 12, and add straight down, and we get negative 17. So the resultant should be 12, negative 17. That's the route, basically, that the actual velocity of this boat would be traveling at. So this is what it's actually going to do. So again, the boat is aiming straight, but the river is pulling it down, and the result is, in fact, what is in green. Okay. So from here, I can get the magnitude and direction that the boat is traveling simply by looking at the arctangent of negative 17 over 12. Let's see what we get for that, because, sorry, that's going to be the arctangent, not the tangent. Okay, so the arctangent of negative 17 over 12. So control divide negative 17 over 12. We get a negative 54.782. But again, I want you to look at this as a positive. So let's say, I'm going to say this is 54.782 as a positive. But that's not what we're going to write here. We're going to write that because my resultant vector is going to help me. Okay, look at that resultant vector. It has a positive x, negative y. So positive x, negative y says it's going to be down here. So my resultant vector is going to be traveling in that fourth quadrant direction, if you will. And this positive 54 represents this nearest x-axis angle. Okay, so now you can either say from here all the way here would be 360 degrees minus that 54 that I got, so 54.7824. Again, remember, you're doing it as far as interpreting it as a positive. And you can say it's traveling at 305.218 degrees, or you could just put the negative there if you'd like. I'm just going to go ahead and now put the negative because it's coterminal, and I can say it's negative 54.782. Now, I know I've been doing a lot of positive angles for all the other examples, but because this is coterminal, you can do this as well. Now let's do a squared plus b squared. Take the square root. Again, remember to put negatives inside parentheses, as you see right here. And you should get that the magnitude is about 20.8. So we're going to say 20.809 units. Okay, so find the actual speed. The speed here was miles per hour. And the reason why I've been wanting you to put units is because here, finally, you're going to say this boat is traveling at 20.809 miles per hour. It's traveling in the direction of either that 305 degrees or this negative 54.782 degrees, and the components are 12, negative 17. So how many degrees was it taken off course? Its original course was here. Its original course was to go into 0. So if it actually ended up traveling this direction, this right here represents, in green, this represents how many degrees it was taken off course. So you can say the boat was taken 54.782 degrees off course. Okay, so let me write that a little bit better. 54.782 degrees off course. All right. So we have these last two problems and then we are done. It says the golfer hits a ball and it hits the ball due east. So we have north, south, east, west. So the golfer hits the ball at 50 miles an hour. We'll say G for golfer. And then however, wind is blowing from the south. So from the south means it's from here going upward. So the wind is going to blow from the south. We'll say the magnitude of W for wind is 12 miles per hour. Find the resultant vector of the ball's velocity. We want to see if the ball's hit here, tail to tip says this is going to be the resultant. This is going to be the pathway of that ball. And it's going to be that G plus W. Okay? And we're trying to find the resultant vector for the ball's velocity. So we're trying to find the magnitude, right here, the magnitude of this velocity, of this resultant, okay? So how does the wind affect the ball's speed and direction? Okay, here we go. So let's build our table, if you will. We have first the golfer, and it's going to be a strength of 50. Direction is 0 degrees because it's going straight to the right, always in unit circle representation. And if we do x times the 50 times the cosine of 0, we'll get 50. If we do 50 times the sine of 0, we'll get 0. So those are the components for the golfer. Okay. Let's now look at the wind. Coming from the south, that means coming from the south, it's traveling at a 90-degree angle. Okay, always from 0 degrees. It's traveling straight up, so it's traveling at a 90-degree angle, unit circle-wise. The strength it gave us was 12, and then we want to do 12 times the sine and 12 times the cosine of 90 degrees. Okay, so in your calculator, you'll just put 12 times the cosine of 90. You get 0, and then you'll say what is 12 times the sine of 90, and you get 12. So another way that you can look at it is whenever they're going up and down, left or right, you see that the pattern is x-wise, depending on whether they're traveling, is going to be that strength itself, or y-wise is going to be that strength itself. Okay. So now let's go to the resultant vector. Okay, so we're going to add these first to get this resultant. We get 50, 12. Visually, we know that the ball is going to travel at a positive x, positive y, otherwise known as a quadrant 1 kind of orientation, if you will. And now we're going to work backwards to get arc tangent of 12 over 50 to get my directional angle. And from that, I get control divide 12 over 50. I get a positive 13.4957. Again, where this is traveling, this is always going to be read as positive. That's the way I want you to look at it. And go to the nearest x-axis. This is 13.496 degrees. Okay? So that, in fact, is the direction that it's traveling at. And then the square root of 50 squared plus 12 squared, take the square root, we get that the strength was 51.4198. So we'll say 420, not degrees. This is going to be miles per hour. So it is traveling, because those are my units, at 51.420 miles per hour in a direction of 13.496 degrees. And these are the components that you got from the resultant from adding straight down. Okay, so find the resultant vector of the ball's velocity. The resultant vector is right here. And then how does the wind affect the ball's speed? Well, it affects it by making it faster than what was hit. Okay, so the wind is helping it go faster than what it was hit with. And also the direction. How does it affect the direction? So the direction is, it threw the ball, basically, if I'm hitting the ball straight this direction and the wind's blowing up, it throws it off just like this last question here that we did before with the boat problem, we're going to say that it throws it off course. So the wind blows the golf ball off course by 13.496 degrees. And that is it for that problem. Because of time, we will do the other one together in class to start class, and then we'll go ahead and go from there as far as for day 4.